Alright, today we're going to be working on a different video lesson. This video lesson today is going to involve a lot more of the chemistry aspect of this stuff. Rather than what we have done a lot before, the stuff that we did in the last chapter was stuff that could apply to solids, liquids, or gases. A lot of when it comes into the second and third law of thermodynamics, you're going to be talking a lot more about gases. Now because of that, we need to reach back into some of the stuff that we've done before and determine a couple of things about gases. Okay? First thing is, in most of the thermodynamic work and all that we're going to be doing in here, we need to work with what are called ideal gases. I'm not sure if there's two S's in gases. If I screwed up, sue me. Alright, ideal gases. Now, there's a few things that you got to realize here. First of all, not everything is ideal. Ideal is absolute best case scenario. Most gases are not going to follow that. But there are a few things that are kind of assumed about a ideal gas. Now first of all, anytime you're talking about anything ideal, ideal always means that that value is theoretical. It does not exist in nature. So because of that, we're going to be using situations that simulate ideal gases. May not exactly simulate them, but they will work for the most part. Okay? Now, it is theoretical, but with ideal gases, you're always going to have three things that are assumed with an ideal gas. First of all, the particle movement has to be random. It cannot be forced. It needs to be something that is kind of left to its own devices. Particle movement has to be random. Secondly, and this is the one that normally throws most ideal gas or most gases from being in the container of ideal, right? An ideal gas must have no particle interaction, which means that they cannot collide with one another. This is the one that is normally this is the one that is normally violated when you end up, well, using this as a simulation rather than an ideal. All right? And the third thing, each individual particle in an ideal gas is considered to be a point particle, meaning that it takes no space, it is just an individual dot. Now, obviously, nothing that exists in nature can be considered a point particle. But in order for the ideal gases to be ideal, they need to fit these three situations. Normally, gases will fit into close enough simulations of this that we can use mathematical means to solve for it. Right? But that's the basics of it. So, there's a few gas laws that are going to relate this stuff all back together here. Alright? Now, once again, all of these laws that I'm about to speak about, they all have to do with the ideal gases. They cannot work if it's not an ideal gas. First one we're going to talk about is Charles' law. Alright? Now, Charles' law has to do with two different variables. Charles' law has to do with the volume and the temperature of a gas. Now, obviously, when you increase the temperature of a gas, you're going to also increase the volume. So what that means is that through Charles' law, there's a direct relationship between volume and temperature of an enclosed gas at constant pressure. Okay? Now, what that looks like mathematically. When we're dealing with Charles' law, that means that the volume of the gas divided by the temperature of that gas is going to equal some constant value. Okay? Now, this equation on its own is pretty much useless. But what it shows you, as this increases, this one must therefore also increase. As this one decreases, this one therefore also must decrease in order to get a constant value coming out. Now, this is practically useless in its current state. What it's best for is looking at the same gas at two different instances in its development. So if you look at the volume at state 1, temperature at state 1 equals whatever the volume of that gas is at state 2, temperature at state 2. So in other words, if you increase the temperature on a known volume of gas to a second temperature, what will be the new volume? Charles' law is an excellent way of getting to that. Okay? Not too difficult on this one. Next one. I'm going to go into Boyle's law. Right, with Boyle's law, Boyle's law relates two different variables. Boyle's law, once again, is going to relate the pressure and the volume of a gas. Now, basically, Boyle's law means that pressure and volume are inversely proportional. Meaning as one goes up, the other goes down. At constant temperature. Okay? So, in this case, we've got pressure times volume is going to equal some constant. Just like with Charles' law. This is practically useless on its own, but if you realize that that constant is going to remain the same no matter what two cases we have here, you'll have P1 V1 equals P2 V2. Okay? That becomes much more useful. Now also realize we have to have this at a constant temperature. Without the constant temperature, it's just not going to work out. So, Boyle's law. And the third one is called Gay-Lussac's law. Right? Now, some books don't worry about this guy too much because a lot of his work actually very, very closely followed Charles. I mean, I'm talking about within 20 years. So because of that, a lot of people ignore Gay-Lussac, but I feel it's important enough to go over. Right? Gay-Lussac's law. All right? With Gay-Lussac, that relates the pressure and the temperature of a gas. Once again, it has to be an ideal gas. All right? Now, in this case, once again, pressure and temperature are directly proportional at constant volume. Alright, now that means as one goes up, the other one goes up. So in this case, once again, it's got to be pressure over temperature equals some constant value. Okay, now with that, same as usual, useless on its own, but if we look at it in two different cases, P1 T1 equals P2 over T2, then it works a lot better. It becomes useful. We can look at this at two different states of the same gas. Okay? Now, a lot of times it's going to be rare that you're able to keep volume constant, pressure constant, or temperature constant. So, there are two other ways that you can relate this stuff back together. Alright? Last two. Combined gas law. Now the combined gas law uses the factors of all three of those laws: Charles' law, Boyle's law, and Gay-Lussac's law. Right? And what that does is it determined that the pressure times the volume of some gas at some temperature is going to equal some constant value. But we can use that the same exact way. P1 V1 over T1 equals P2 V2 over T2. Okay? This same exact thing, working through the same exact situation. Alright? So if you have those three things, it's a very good thing. Now, other times, what's going to matter is the amount of material you have. If you're dealing with a mass, then this stuff here is pretty much useless. So, key thing to remember here, right? If you're just dealing with P, V, and T, then you should use one of those four laws I just gave you. Use Boyle's, Charles', Gay-Lussac's, or the combined gas law. Okay? Now, if they instead give you a mass or a number of moles, then you need to use what's called literally the ideal gas law. All right? Now, with the ideal gas law, this takes everything and puts it in ratio form and tells you how much material you actually have. So the ideal gas law breaks down to this. Probably worked with this already in chemistry, but kind of a refresher. Pressure times volume equals number of moles, constant temperature. Okay? So, basically, everything else that we've talked about still is involved in this. Alright? Pressure and temperature are inversely proportional. So if I take this, divide it both sides, I end up getting, pressure and temperature are directly proportional. Get P over V, P over T, V over T. Alright? P times V. All those things are still factored into here. But now we've got two different things here. We've got N and we've got R. N is simply just the number of moles. That tells you how many individual particles of gas you have there. Alright? And once again, if you're not so sure about moles, if it's been a while, 1 mole equals 6.02 times 10 to the 23rd particles. Okay? So, might have to be some unit conversion stuff like that in there. Now R is what's called the rate constant. Once again, this R value, based upon what you're given the other variables in terms of, is going to have a slightly different number. I'm not going to force you to memorize them all, but I am going to force you to memorize one or two, and I am going to ask you to try to remember the conversions. Alright, it's going to go joules to calories, stuff like that. Not incredibly difficult, but it's one of those things that can be very useful in going from one form to another. It can make a difference between a problem being very easy and a problem being very difficult. When you are done, when you're done with this video, come back over here. I should have a worksheet ready for you to work on. We'll see how it goes from there. Alright, but this is kind of the start of the new stuff. From here, we're going to be able to get into entropy, or basically the amount of chaos in a system. We'll get into enthalpy, a whole bunch of different stuff, and but this is kind of the bread and butter of it. You have to understand this stuff. You need to be able to move from one form into another before you can go much further. Right? Das ist alles. So the mass, once again, is going to be 0.150. Pardon me, I forgot to fill in the units on this. Kilograms. Temperature change is 50 degrees Celsius, but 50 degrees Celsius is equal to 50 Kelvin. So, double checking units here. Kelvin cancels. Kilograms cancel. I'm left with kilojoules. So at this point, I multiply 333 times 0.150. got 49.95 kilojoules required in order to melt that ice. So the Q of the ice equals 49.95 kilojoules plus whatever heat is required to lift it to that next temperature. So now it's going to be 0.150 times 50 Kelvin times 4.180 equals 31.35. Okay? So 31.35 kilojoules. So my total Q of ice, which is the heat that needs to be gained by the ice, is 49.95 plus 31.35. 81.3.